Right now, at this very moment, there might be 7 invisible dimensions passing through your body. They're smaller than an atom, curled up tighter than anything you could ever imagine, and yet they might hold the key to understanding everything in our universe. Close your eyes, take a deep breath, and let me take you on a journey through the hidden fabric of reality itself. You see, for most of human history, we've lived in a world that seemed simple enough to understand. We move forward and backward, left and right, up and down. 3 dimensions of space, stretching out infinitely in all directions. And then there's time, that 4th dimension always moving forward, carrying us from one moment to the next. 4 dimensions total. That's our reality, or at least that's what we thought. But what if I told you that this might be just the beginning? What if the universe is far stranger, far more complex, far more beautiful than we ever imagined? What if there are dimensions we can't see, can't touch, can't even properly imagine, hidden away in the very fabric of space itself? Let's start our journey slowly, gently, at the very beginning. Picture yourself standing in a vast, empty space. Nothing around you but darkness. Now imagine a single point of light appearing in front of you. Just a dot floating in the void. This point has no dimension at all. It's 0-dimensional. It exists, but it has no length, no width, no height. It simply is. Now watch as that point begins to move, leaving a trail of light behind it. It draws a line through space, stretching from here to there. This line has length now. It goes from one place to another. This is the 1st dimension. If you were a creature that could only move along this line forward or backward, that would be your entire universe. Just a line stretching out in one direction. But we know there's more, don't we? Imagine that line now moving sideways, sweeping across space, creating a flat surface. A sheet of light stretching out in 2 directions. Length and width. This is the 2nd dimension. A flat world like a piece of paper floating in the darkness. Creatures living on this sheet could move forward and backward, left and right, but they would have no concept of up or down. Their entire universe would be flat, pressed against this 2-dimensional surface. And now, let that sheet rise upward, or sink downward, expanding into the 3rd dimension. Suddenly, space has depth. There's up and down a whole new direction to explore. This is the world we know, the world we live in. 3 dimensions of space, giving us the rich, complex, 3-dimensional reality we experience every day. But here's where things get interesting. In the early 20th century, a man named Albert Einstein showed us that space and time aren't separate things at all. They're woven together into a single fabric, a 4-dimensional tapestry called space-time. Time isn't just something that happens while space exists. Time is a dimension itself, intertwined with the 3 dimensions of space in ways that still make our heads spin when we really think about it. Einstein showed us that massive objects like stars and planets actually bend this fabric of space-time, creating the force we call gravity. It's not that the Earth pulls on you with some invisible force. It's that the Earth's mass warps the space-time around it, and you're simply following the curved path through that warped space. It's beautiful, elegant, and completely changed how we understand the universe. 4 dimensions, 3 of space, 1 of time. That should be enough, shouldn't it? That should be the complete picture of reality. But nature, as we've learned again and again, is rarely satisfied with simple answers. In the 1920s, a mathematician named Theodore Kaluza had a wild idea. He was working on Einstein's equations, trying to understand how gravity works, when he decided to do something unusual. What if, he thought, there was actually a fifth dimension? Not just 3 dimensions of space and 1 of time, but 4 dimensions of space and 1 of time. 5 dimensions total. When he worked out the mathematics, something extraordinary happened. Einstein's equations for gravity, which describe how massive objects bend space-time, suddenly included something extra. Something that looked exactly like the equations for electromagnetism, the force that governs electricity, magnetism, and light itself. Just by adding 1 extra dimension, Kaluza had seemingly unified 2 of the fundamental forces of nature into a single mathematical framework. There was just one problem. Where was this 5th dimension? We can see 3 dimensions of space all around us. We experience time flowing from past to future. But where was this mysterious 5th dimension hiding? A few years later, a physicist named Oscar Klein suggested an answer. What if, he proposed, this extra dimension wasn't stretched out large like the dimensions we know? What if it was curled up, wrapped around itself so tightly that we could never see it? Imagine taking a long piece of paper and rolling it into a tiny tube, so small that from far away it looks like a one-dimensional line, but up close there's actually a hidden dimension curled around it. That, Klein suggested, is what the 5th dimension might be like, curled up so small, so incredibly tiny, that we simply can't perceive it. How small? Unimaginably small. Klein calculated that this dimension would need to be curled up at a scale called the Planck length, which is about 10 billion times smaller than an atom. At that scale, it would be completely invisible to us, hidden away in the microscopic structure of space itself. For decades, this idea of Kaluza and Klein remained a curious footnote in physics. Interesting, perhaps, but not something that could be tested or proven. The universe seemed to work perfectly fine with just 4 dimensions, and there was no compelling reason to believe in hidden ones. But then, in the 1960s and 1970s, physicists began to discover something troubling. The more they learned about the fundamental particles and forces that make up our universe, the more complicated things became. There were 4 fundamental forces: gravity, electromagnetism, the strong nuclear force that holds atomic nuclei together, and the weak nuclear force responsible for certain types of radioactive decay. There were dozens of different types of particles: electrons, quarks, neutrinos, photons, and many more. And nobody could understand how it all fit together. Physicists tried to build theories that could explain all these particles and forces in a unified way, but nothing seemed to work. Every theory had problems, contradictions, mathematical infinities that made the equations meaningless. It seemed like the more we learned about the universe at its smallest scales, the less sense it made. Then, in the 1980s, a remarkable idea emerged. It was called string theory, and it suggested something radical. What if the fundamental building blocks of the universe weren't particles at all? What if, at the very smallest scales, everything in the universe was made not of tiny points, but of tiny vibrating strings? Imagine a violin string stretched tight between 2 points. Pluck that string, and it vibrates, creating a musical note. Pluck it differently, and you get a different note. Same string, different vibration, different sound. String theory proposed that reality works the same way. Every particle we see, every electron and quark and photon, is actually a tiny string vibrating in a particular pattern. An electron is a string vibrating one way. A quark is a string vibrating another way. All the diversity of the universe, all the different types of particles and forces arise from these strings vibrating in different patterns. It was a beautiful idea, elegant and simple. But there was a catch. When physicists worked out the mathematics of string theory, they discovered something strange. The equations only made sense, only worked properly, only avoided those troublesome mathematical infinities. If the universe had more than 4 dimensions, not 5 dimensions, not 6, the mathematics demanded 10 dimensions, 9 dimensions of space plus time, 6 dimensions beyond the 4 we know and experience, 6 hidden dimensions curled up and invisible, woven into the fabric of reality at scales so small we could never hope to see them directly. It seemed absurd. How could there be 6 entire dimensions of space that we're completely unaware of? How could they be hidden from us so completely? But as physicists explored string theory further, they realized that these extra dimensions weren't just a mathematical curiosity. They were essential. The way these extra dimensions were curled up, the shapes they formed, the geometry of these hidden spaces, determined everything about our universe. The types of particles that exist, the strengths of the fundamental forces, even the physical constants that govern how nature works. All of these emerged from the geometry of the extra dimensions. Think of it like this. Imagine a flute. When you blow air across the opening, the column of air inside the flute vibrates, creating sound. But the pitch of that sound depends on the length of the column. Cover different holes on the flute and you change the length, creating different notes. Same air, same basic mechanism, but different geometry creates different results. The extra dimensions in string theory work the same way. The strings vibrate, creating particles, but the exact properties of those particles depend on the geometry of the hidden dimensions they're vibrating through. Different geometries create different particles, different forces, different physical laws. This means that the reason our universe is the way it is, the reason electrons have the mass they do, the reason gravity is so much weaker than the other forces, the reason atoms can form and chemistry can happen and life can exist, all of this might be determined by the precise shape of 6 hidden dimensions we can't even see. It's a staggering thought. These invisible dimensions, curled up smaller than we can imagine, might hold the key to understanding everything about our reality. But string theory didn't stop at 10 dimensions. As physicists refined the theory through the 1990s and 2000s, they discovered it was even stranger than they thought. There wasn't just one version of string theory. There were 5 different versions, each with slightly different mathematics, each describing strings in slightly different ways. For a while, this seemed like a problem. Which version was correct? Which one described our universe? But then physicists realized something remarkable. All 5 versions of string theory, plus another theory called supergravity, were actually different faces of the same underlying theory. They called this deeper theory M theory, and it required 11 dimensions. 10 dimensions of space plus time, 11 dimensions total. 7 dimensions hidden away beyond the 4 we experience. 7 invisible directions woven into every point in space, too small to see, too complex to visualize, but potentially fundamental to the very existence of our universe. Now you might be wondering, how can we possibly talk about dimensions we can't see? How can physicists make any claims about spaces too small to measure? Isn't this all just mathematical fantasy untethered from reality? It's a fair question, and the truth is, we don't have direct evidence for these extra dimensions. We can't point a telescope at them or build a microscope powerful enough to see them. They're hidden at scales far beyond our current ability to probe. But that doesn't mean they're pure speculation. String theory and M-theory aren't just made-up stories. They're rigorous mathematical frameworks that make specific predictions about how the universe should work. And remarkably, many of these predictions match what we observe in nature. String theory naturally incorporates gravity, something that previous theories struggled with. It predicts the existence of certain types of particles that we've since discovered. It provides potential explanations for deep mysteries in physics, like why the universe has the particular mix of particles and forces that it does. More than that, string theory has revealed deep mathematical connections between seemingly unrelated areas of physics and mathematics, connections that continue to surprise and inspire physicists and mathematicians today. Even if string theory ultimately turns out not to be the complete description of nature, the mathematics it's revealed is undeniably beautiful and profound. But let's step back for a moment. Let's return to this idea of hidden dimensions and really try to understand what it means. How can a dimension be hidden? How can it be so small that we can't perceive it? Let me offer you an analogy. Imagine you're an ant walking along a tightrope stretched between two poles. From your perspective as a tiny ant, the tightrope is your entire universe. You can move forward along the rope or backward along the rope. That's it. One dimension of space. The rope might as well be an infinite line stretching out in both directions. But now imagine you have sharper eyes powerful enough to see the true structure of the tightrope. You'd realize that it's not actually a one-dimensional line at all. It's a cylinder, a tube with a second dimension wrapped around it. You could walk not just along the length of the rope, but around its circumference. That second dimension was always there. You just couldn't perceive it because you were too large compared to the rope's thickness, or rather, because the rope's thickness was too small compared to your size. This is what physicists mean when they talk about extra dimensions being curled up or compactified. These dimensions aren't hidden in the sense that they're in some other place. They're right here, at every point in space, woven into the fabric of reality. But they're curled up so incredibly small that we simply can't perceive them. We're like ants on a rope so thin that we can't detect its thickness, moving through a universe that seems to have only 3 large dimensions of space, unaware of the additional dimensions curled up beneath our notice. The question then becomes, what shapes do these hidden dimensions take? When you curl up a dimension, it has to wrap around itself somehow, forming some kind of geometric structure. In string theory and M-theory, these structures are called Calabi-Yau manifolds, named after the mathematicians Eugenio Calabi and Xing-Tung Yau, who studied them. Calabi-Yau manifolds are extraordinarily complex geometric shapes existing in 6 or 7 dimensions. They're beautiful, intricate, with elaborate structures and symmetries that mathematicians are still working to understand. And according to string theory, one of these manifolds, with precisely the right shape and properties, is attached to every single point in our 3-dimensional space. Imagine it. Right where you're sitting, right at the tip of your finger, right in the empty space in front of you, there's a tiny Calabi-Yau manifold, a six-dimensional geometric shape curled up smaller than the smallest thing you can imagine. And not just one. Trillions upon trillions of them, one at every point in space, forming a hidden landscape that permeates our entire universe. The specific shape of these manifolds matters immensely. Different shapes would lead to different types of particles, different forces, different physical laws. Finding the right Calabi-Yau manifold, the one whose geometry produces exactly the particles and forces we see in our universe, is one of the great challenges of string theory. And here's where things get even more interesting. Physicists have discovered that there are an enormous number of possible Calabi-Yau manifolds. Current estimates suggest there might be as many as 10 to the 500th power different possible shapes. That's a 1 followed by 500 zeros. It's a number so large that if you tried to explore one new possibility every second, you wouldn't finish even if you had the entire age of the universe multiplied by trillions of times over. This vast collection of possibilities is sometimes called the string theory landscape. Each different Calabi-Yau manifold represents a different possible universe with different particles, different forces, different laws of physics. Our universe, with its particular particles and forces, corresponds to one specific shape somewhere in this vast landscape. But which one? And why that one rather than any other? These are questions physicists are still grappling with. Some suggest that all of these possibilities might actually be realized somewhere in a vast multiverse where different regions of space have different compactifications, different hidden dimensions, and therefore different physical laws. In this view, our universe with its particular properties isn't special. It's just one of countless universes, each with its own version of physics determined by how the extra dimensions are curled up in that region. This is speculative, of course. We have no direct evidence for other universes or for the specific shape of the extra dimensions in our own universe. But it's a logical possibility that emerges from the mathematics, and physicists take it seriously. Now, you might be wondering, if these extra dimensions are so small and hidden, does it really matter whether they exist or not? Does it change anything about our daily lives or our understanding of the universe we can actually see and experience? In some ways, no. The extra dimensions, if they exist, are so small and so tightly curled up that they have almost no direct effect on anything at the scales we experience. Your body isn't going to suddenly slip into a hidden dimension. Objects aren't going to vanish into some fifth-dimensional space. For all practical purposes, we can continue living our lives as if there are only 4 dimensions. But in a deeper sense, yes, it matters profoundly, because these hidden dimensions, invisible as they are, might be the reason our universe is capable of supporting complexity, structure, chemistry, and life. They might be the hidden architecture underlying all of reality, the secret scaffolding that makes everything else possible. Think about it. The fact that atoms are stable, that electrons orbit nuclei in predictable ways, that molecules can form and chemical reactions can occur, all of this depends on the precise properties of particles and forces. And those properties, according to string theory, emerge from the geometry of extra dimensions. Change the shape of those hidden dimensions, even slightly, and you might have a universe where atoms can't form, or where the only atoms that can form are hydrogen, with no possibility of complex chemistry. or where forces are so strong or so weak that stars can't shine, planets can't form, and life has no chance to arise. In this view, we're only here, only able to contemplate these questions, because we happen to live in a region of space where the extra dimensions are curled up in just the right way to allow our existence. It's a profound thought. The hidden architecture of reality, invisible and intangible, might be perfectly tuned to make our universe a place where consciousness can emerge and wonder about its own origins. But let's not get too lost in philosophical speculation. Let's return to the science, to the question of whether these extra dimensions really exist, and how we might ever hope to find out. One approach is indirect. If extra dimensions exist, they should have subtle effects on the behavior of particles and forces, even if we can't see the dimensions themselves. For example, gravity might behave slightly differently than we expect at very short distances. If we could measure gravitational forces at scales approaching the size of the compactified dimensions, we might see deviations from Einstein's predictions, hints of the extra dimensions influencing how gravity works. Unfortunately, this is extraordinarily difficult. The scales we're talking about are so small that our best experiments can't probe them. We can test gravity at scales of about 1/10 of a millimeter, which is tiny by everyday standards, but still enormous compared to the Planck scale where extra dimensions might be hiding. Reaching those scales would require energies and technologies far beyond anything we currently possess. Another approach involves particle accelerators like the Large Hadron Collider. When particles collide at extremely high energies, they probe the structure of space at very small scales. If extra dimensions exist, some of that collision energy might leak into those dimensions, disappearing from our three-dimensional space. By carefully measuring the energy and momentum of particles before and after collisions, physicists can look for missing energy that might have escaped into extra dimensions. So far, they haven't found any definitive evidence, but they keep looking, refining their experiments, pushing to higher energies and greater precision, hoping to catch a glimpse of something beyond the 4 dimensions we know. There's also a fascinating possibility involving black holes. In a universe with extra dimensions, the physics of black holes changes. It becomes easier to create tiny black holes, microscopic objects that form when matter is compressed to extreme densities. These tiny black holes would be unstable, evaporating almost instantly in a burst of radiation through a process called Hawking radiation. If extra dimensions exist and are larger than some theoretical models suggest, particle accelerators might actually be able to create these microscopic black holes. Before you panic, let me reassure you, these would be completely harmless. They'd be far too small and short-lived to pose any danger. They'd evaporate in a tiny fraction of a second, leaving behind only a characteristic pattern of particles that physicists could detect. Finding such black holes would be extraordinary evidence for extra dimensions. So far, we haven't seen them, but the search continues, and with each experiment that finds nothing, we learn something valuable. We constrain the possibilities, narrowing down the range of where extra dimensions could be hiding and how large they might be. There's something beautiful about this process, this patient exploration of the unknown. Physicists build theories, make predictions, design experiments, and test those predictions against reality. Sometimes they find what they're looking for. More often they don't. But even negative results tell us something, helping us refine our understanding and guide future searches. Let me take you deeper into the mathematics now, gently, carefully, not with equations, but with concepts. What does it really mean for space to have 10 or 11 dimensions? How can we even begin to think about such a thing? Let's start with something simpler. Think about a cube. A cube is a three-dimensional object. It has length, width, and height. Now imagine a square. A square is a two-dimensional object, a flat shape with length and width, but no height. You can think of a cube as being made up of squares, 6 of them arranged in three-dimensional space to form the cube's faces. Now here's a mind-bending thought. In the same way that a three-dimensional cube is made up of two-dimensional squares, a four-dimensional object called a hypercube or tesseract is made up of three-dimensional cubes. You can't visualize this directly because we don't experience 4 dimensions of space, but mathematically it's perfectly well defined. A tesseract is to a cube what a cube is to a square, and we can keep going. A 5-dimensional object is made up of 4-dimensional objects. A 6-dimensional object is made up of 5-dimensional objects, and so on, extending up to any number of dimensions you like. The mathematics doesn't care that we can only visualize 3 dimensions. It works just as well in 10 dimensions or 11 or a million. This is how physicists think about extra dimensions, not as something we can visualize or picture, but as mathematical spaces that exist in the abstract realm of equations and numbers. These spaces have properties, geometric structures, symmetries, and relationships that can be studied and understood, even if we can't draw them on a piece of paper or build a model of them. Calabi-Yau manifolds, those 6-dimensional shapes that might represent the hidden dimensions in string theory, are examples of such mathematical spaces. They're defined by equations, by properties that the coordinates must satisfy, by symmetries and topological features. Mathematicians have studied them extensively, not because they thought they had anything to do with physics, but simply because they're beautiful and interesting mathematical objects. The fact that these purely mathematical constructs might turn out to describe the actual hidden structure of physical space is one of those remarkable coincidences that makes you wonder about the deep connection between mathematics and reality. Why should abstract mathematical objects, studied for their own sake, turn out to have physical significance? It's a question that philosophers and physicists have pondered for centuries, and we're no closer to an answer. But let's not lose ourselves in philosophy. Let's stay grounded in the physics and the actual theories and ideas that physicists have developed. One important concept in string theory is something called moduli. These are parameters that describe how the extra dimensions are curled up. Think of them as knobs you can turn to change the size and shape of the compactified dimensions. Turn one knob and the dimensions might become slightly larger. Turn another and their shape might change, becoming more elongated or more symmetrical. The interesting thing is that these moduli aren't fixed. In principle, they can change over time or vary from place to place. This means that the properties of particles and forces, which depend on the shape of the extra dimensions, might also change over time or vary across the universe. This is a startling possibility. We tend to think of physical constants as truly constant, unchanging throughout all of space and time. But if the extra dimensions can change their configuration, then what we call constants might not be constant at all. They might have been different in the early universe, or they might be different in distant regions of space. Physicists have looked for evidence of changing constants, examining light from distant galaxies that's been traveling through space for billions of years, looking for any sign that the fine structure constant or other fundamental parameters were different in the past. So far, they've found no compelling evidence of change. The constants seem to be truly constant, at least within our observable universe and over the time scales we can measure. This tells us something. If extra dimensions exist and if their configuration determines physical constants, then either those dimensions are locked into a very stable configuration, or there's some mechanism we don't understand that keeps them fixed. It's another clue, another piece of the puzzle, even if we don't fully understand what it means yet. Let's talk about supersymmetry for a moment. This is another key idea in string theory and M-theory. Supersymmetry is a mathematical symmetry that relates particles of different types. In a supersymmetric universe, every particle has a superpartner with slightly different properties. Electrons would have selectrons. Quarks would have squarks. Photons would have photinos. These superpartners haven't been discovered yet. If they exist, they must be much heavier than the ordinary particles we know, which is why we haven't seen them in our experiments. But supersymmetry is essential to string theory. Without it, the mathematics doesn't work. The theory becomes inconsistent, plagued with infinities and contradictions. Supersymmetry also has a beautiful property. In a supersymmetric universe, certain calculations that would otherwise be impossibly difficult become tractable. The mathematics simplifies in elegant ways, allowing physicists to explore aspects of string theory that would otherwise be inaccessible. But here's the puzzle. If supersymmetry is fundamental to string theory, why don't we see it in nature? Why haven't we found these superpartner particles? There are several possible explanations. Maybe supersymmetry exists but is broken at the energies we can currently probe, hiding the superpartners just beyond our reach. Maybe supersymmetry is broken at such high energies that we'll never be able to access them with our technology. Or maybe supersymmetry, beautiful as it is mathematically, simply isn't part of our universe's actual physics. This is one of the great open questions in particle physics. The Large Hadron Collider has been searching for supersymmetric particles for over a decade now, and so far, nothing. Every experiment that comes back empty-handed makes it a little less likely that supersymmetry exists in the simple forms that physicists originally hoped for. But the search continues, because if those superpartners are out there, finding them would be one of the greatest discoveries in the history of science. Let me take you now to a different aspect of extra dimensions, something called brane worlds. In string theory, strings aren't the only objects that exist. There are also higher dimensional objects called branes, short for membranes. Just as a string is a one-dimensional object that can vibrate, a brane is a two-dimensional, three-dimensional, or even higher dimensional object that can also vibrate and move through space. Our universe and some versions of string theory might actually be a three-dimensional brane floating in a higher dimensional space. All the particles and forces we experience might be confined to this brane, stuck on its three-dimensional surface like ants on a sheet of paper. The extra dimensions would be directions perpendicular to our brane, directions we can't move in, but that nonetheless exist. This is called the brane world scenario, and it leads to some fascinating possibilities. For example, gravity might not be confined to our brane the way other forces are. Gravity might be able to leak out into the extra dimensions, spreading through the higher dimensional space. This would explain why gravity is so much weaker than the other forces. Not because gravity itself is inherently weak, but because most of its strength is dispersed into dimensions we can't access. In this picture, two brains might exist in the same higher dimensional space, floating near each other, but separated by a tiny gap in an extra dimension. These two brains would be entire universes, complete with their own particles, forces, and physical laws. They could be right next to each other in the extra-dimensional direction, just a microscopic distance apart, and yet completely unable to interact except through gravity, which can leak across the gap. This raises the astonishing possibility that there might be another universe, another three-dimensional space full of matter and energy, floating right next to ours in an extra dimension. We can't see it, can't touch it, can't detect it directly, because photons and all other particles are confined to our brain. But it might be there nonetheless, a parallel world separated from ours by the thinnest of gaps in a hidden dimension. Is this true? We don't know. It's speculation based on the mathematics of string theory and brain worlds. But it's a logically consistent possibility, and physicists take it seriously enough to think about how we might test it. If such parallel brains exist, they might have subtle gravitational effects on our universe. They might influence the expansion of space or leave imprints in the cosmic microwave background radiation left over from the Big Bang. So far, we've seen no evidence of such effects. But the cosmos is vast and full of mysteries, and we've only begun to understand its deepest workings. Let's turn now to one of the most profound questions these ideas raise, the nature of the Big Bang itself. In standard cosmology, the universe began 13.8 billion years ago in an infinitely dense, infinitely hot state. Space and time themselves came into existence at that moment. There was no before the Big Bang because time itself didn't exist yet. But in string theory and M theory, with their extra dimensions and brain worlds, new possibilities emerge. Perhaps the Big Bang wasn't the absolute beginning of everything. Perhaps it was an event within a larger pre-existing cosmos. Perhaps our universe began when two brains collided in the higher dimensional space, and the energy of that collision created all the matter and energy in our three-dimensional world. This is called the ekpyrotic scenario, from a Greek word meaning conflagration. In this picture, brains float through the higher dimensional bulk space, occasionally colliding. Each collision creates a new universe, a new three-dimensional brain filled with hot matter and radiation that then expands and cools, forming galaxies, stars, and planets. Our Big Bang in this view was just one of many such collisions, one moment in an eternal cycle of brain collisions and universe creation. Before our universe existed, there might have been other universes, other Big Bangs stretching infinitely far into the past. And in the future, there might be more collisions, more universes born from the collision of brains in dimensions we can't perceive. Again, this is speculative. We have no direct evidence for brain collisions or cyclic universes. But the mathematics allows for such scenarios, and physicists explore them to see what predictions they might make that could be tested against observations. One interesting prediction of some of these models is that they produce a slightly different pattern of temperature fluctuations in the cosmic microwave background than standard Big Bang theory predicts. Astronomers have measured these fluctuations with exquisite precision using satellites like WMAP and Planck. So far, the observations match standard theory beautifully. But as measurements become ever more precise, perhaps we'll see subtle deviations that point towards something more exotic happening in those first moments of our universe's existence. Let me bring you back now to a more fundamental question. Do these extra dimensions truly exist? Or are they just mathematical artifacts, useful fictions that help us organize our equations but don't correspond to anything real? This is a deep philosophical question, and honest physicists will tell you they don't know the answer. The extra dimensions of string theory are required by the mathematics. Without them, the theory doesn't work. But whether those mathematical dimensions correspond to actual physical spaces is something we can't say for certain without experimental evidence. Some physicists take a pragmatic view. If string theory successfully describes nature, if it makes predictions that match experiments, then the extra dimensions are as real as anything else in physics. After all, we don't directly perceive quantum wave functions or space-time curvature either, but we consider them real because theories involving these concepts successfully describe observations. Others are more cautious. They argue that we should distinguish between the mathematical structure of our theories and the actual nature of reality. Just because a mathematical model works doesn't mean every element of that model corresponds to something physical. The extra dimensions might be calculational tools, useful for organizing the mathematics, but not literal spaces that exist in reality. This debate touches on one of the oldest questions in philosophy. What is the relationship between mathematics and physical reality? Are mathematical structures discovered or invented? When physicists find that a particular mathematical framework describes nature, does that mean nature is fundamentally mathematical, or just that mathematics is a powerful language for describing patterns? These are questions without clear answers, but they're worth pondering as you drift toward sleep, letting your mind wander through these abstract spaces and possibilities. Let me tell you about one more fascinating aspect of extra dimensions: their connection to black holes. In four-dimensional space-time, black holes are well understood. They're regions where gravity is so strong that nothing, not even light, can escape. They're described by elegant solutions to Einstein's equations, and we've even photographed them, capturing images of the glowing matter swirling around their event horizons. But in higher dimensions, black holes become far stranger. In a universe with extra dimensions, black holes would have different properties. Their event horizons would have different shapes. They'd radiate Hawking radiation differently. And most intriguingly, they'd reveal information about the hidden dimensions through the precise pattern of that radiation. There's a deep connection here, discovered through what's called the ADS-CFT correspondence, which relates gravitational theories in one number of dimensions to quantum field theories in one fewer dimension. This correspondence has revealed that black holes in higher dimensional spaces are intimately connected to the behavior of quantum systems in lower dimensions. It's a profound result that's still being explored, connecting quantum mechanics, gravity, and the geometry of extra dimensions in unexpected ways. Some physicists believe that understanding this connection might help solve one of the greatest puzzles in theoretical physics, the black hole information paradox. When matter falls into a black hole, it seems to disappear completely. But quantum mechanics says information can't be destroyed. So where does the information go? Is it somehow encoded in the black hole's Hawking radiation? Is it stored in subtle correlations in the extra dimensions? These are active areas of research, and the answers might depend crucially on the nature of extra dimensions and how information can be encoded in higher dimensional spaces. As you lie here, drifting between waking and sleeping, imagine yourself shrinking down, becoming smaller and smaller. You pass through the scale of everyday objects, then cells, then atoms, then atomic nuclei, then the quarks inside protons and neutrons. You keep shrinking, 1 billion times smaller, 1 trillion times smaller, down to the Planck scale, the smallest meaningful distance in physics. At this scale, space itself becomes quantum, fluctuating, and uncertain. And here, at the very edge of what we can conceptualize, the extra dimensions might reveal themselves, not as empty spaces, but as complex geometric structures, Calabi-Yau manifolds, curled up tighter than the tightest knot, yet containing within their geometry all the information that determines how particles behave and forces operate. You're at every point in space right now. These structures exist. In the air you breathe, in your body, in the earth beneath you and the stars above. Hidden dimensions, invisible and intangible, yet potentially fundamental to everything that exists. It's a humbling thought. Our entire three-dimensional universe, with all its vastness, its hundreds of billions of galaxies, each containing hundreds of billions of stars, might be just a small part of a much larger reality. We're like creatures living on the surface of an ocean, aware only of the 2 dimensions we can move across, completely unaware of the depth beneath us. But we're fortunate to live in an age when we can at least glimpse the possibility of those depths. When we have the mathematics and theories to describe what we cannot see, when we can push the boundaries of knowledge even without being able to directly perceive what lies beyond. The search for extra dimensions continues. Physicists around the world are designing new experiments, building more powerful particle accelerators, analyzing data from cosmic rays and astronomical observations, always looking for that telltale sign that space has more dimensions than meet the eye. Maybe they'll find something. Maybe in your lifetime there will be a discovery, a signal in the data that can only be explained by extra dimensions. Or maybe the extra dimensions, if they exist, are hidden so thoroughly that we'll never be able to prove their existence directly, and they'll remain beautiful mathematical constructs, tantalizing possibilities that we can describe but never truly confirm. Either way, the journey of exploring these ideas, of pushing the boundaries of human knowledge and imagination, is worthwhile in itself. We're creatures who wonder about our place in the cosmos, who ask deep questions about the nature of reality, who aren't satisfied with surface appearances but want to understand the fundamental structure of everything. That impulse, that curiosity, has driven every great advance in human understanding, from the ancient Greeks who first realized the earth is round, to Galileo discovering moons around Jupiter, to Einstein revealing the curved nature of space-time, to modern physicists probing the possibility of hidden dimensions. Each generation stands on the shoulders of those who came before, seeing a little farther, understanding a little more deeply. And you, lying here in the darkness, listening to these words, you're part of that tradition. By thinking about these ideas, by letting your mind explore possibilities beyond everyday experience, you're engaging with some of the deepest questions humans have ever asked. You're reaching toward an understanding of reality that goes far beyond the surface appearance of things. So let your mind rest now. Let these ideas drift through your thoughts like clouds across a night sky. Extra dimensions, hidden spaces, curled up geometries, parallel brains, the vast string theory landscape. Let them wash over you gently, not trying to grasp or understand everything, just letting yourself be carried along by the wonder of it all. Somewhere out there, or perhaps right here in spaces too small to see, reality might be far richer and stranger than we ever imagined. The universe might have depths we can barely begin to conceive, and that's beautiful. That's something worth contemplating as you drift towards sleep. There's a comfort in mystery, in knowing that not everything is understood, that there are still frontiers to explore, questions to ask, discoveries waiting to be made. We haven't figured everything out. The universe still has secrets, and some of those secrets might be hidden in dimensions we can't even perceive, woven into the fabric of space at scales smaller than we can imagine. Perhaps as you sleep tonight, your dreams will take you through higher dimensional spaces, through impossible geometries and alien landscapes. Perhaps you'll fly through a Calabi-Yau manifold, soaring along its curved surfaces and through its twisted corridors. Perhaps you'll stand on a three-dimensional brain and look across the gap into another universe, parallel to ours but forever separated. Or perhaps you'll simply rest, your mind quiet and peaceful, letting the day's thoughts settle like dust after a storm. Either way, know that you've touched something profound, something at the very edge of human knowledge and understanding. The hidden dimensions, if they exist, have been there all along, invisible companions to every moment of your life. They've been there in every breath you've taken, every step you've walked, every thought you've thought. They're part of the deep structure of reality, the hidden architecture underlying everything. And maybe, just maybe, understanding that fact, contemplating the possibility that reality is far richer than it appears, will give you a sense of wonder that carries into your dreams and into tomorrow. So close your eyes now. Let yourself sink deeper into rest. The hidden dimensions will still be there in the morning, still wrapped up in space, still keeping their secrets. But for now, let them go. Let your thoughts become quieter, slower, softer. Feel the weight of your body against the bed. Feel the gentle rhythm of your breathing. In and out, like waves on a shore. Each breath carrying you deeper into relaxation, deeper into peace. The three dimensions, you know, are enough for now. Length and width and height, the familiar coordinates of everyday existence. You don't need to perceive the extra dimensions to rest in them. They're there, all around you, holding you in their invisible embrace. Space itself, all of space, every point from here to the farthest galaxy, might be riddled with these hidden dimensions, these curled up spaces too small to see. And in those spaces, strings vibrate, creating all the particles and forces that make up our world, creating the atoms in your body, the neurons in your brain, the thoughts in your mind. You are made of strings, perhaps, tiny vibrating loops of energy, resonating through both the dimensions you know and the dimensions you don't. And that's a beautiful thought to fall asleep with. You're not just a collection of atoms. You're a symphony of vibrations in a 10-dimensional or 11-dimensional space, a pattern of energy dancing through hidden geometries. Let that image fill your mind as you drift deeper. Strings vibrating, dimensions curling, space extending in directions you cannot see, but that support and contain your existence nonetheless. The mathematics continues whether you're awake or asleep. The extra dimensions, if they're real, don't depend on anyone perceiving them. They simply are, woven into the fabric of reality, doing their silent work of making the universe function the way it does. And you can rest in that. Rest in the knowledge that the universe is far larger and stranger than it appears. Rest in the mystery, in the unknowing, in the vast spaces of possibility that still exist in our understanding. Scientists will continue their work tomorrow. They'll analyze data, refine theories, design new experiments. They'll search for evidence of extra dimensions in particle collisions and gravitational waves and the light from distant stars. And maybe someday they'll find something definitive, or maybe the mystery will deepen, revealing even more questions than answers. But tonight, none of that matters. Tonight you can simply be, simply exist in this three-dimensional space, breathing this air, resting on this bed, while hidden dimensions surround you, invisible and silent. Let yourself become heavier now. Let every muscle relax, let every thought slow down. There's nothing you need to do, nothing you need to figure out. The universe will keep its secrets a little longer, and that's perfectly fine. Imagine yourself floating in space, but not the black void you might picture. Imagine floating in a rich, multi-dimensional space, with directions extending not just in the familiar 3 dimensions, but in 6 or 7 others, curled up tight around you, holding you, supporting you. You can't see them, can't move in them, but they're there, part of the hidden architecture of reality. And in some strange way, they're part of you too, because you exist in them, because the particles that make up your body move through them, vibrate through them, are shaped by their geometry. You're connected to the deepest structure of the cosmos, to the very fabric of space and time, and whatever other dimensions might exist. You're not separate from the universe. You're woven into it, part of its pattern, part of its dance. And as you sleep, that dance continues. Strings vibrate in 10 dimensions. Brains float through higher dimensional spaces. The universe expands, carrying galaxies away from each other, while at the smallest scales, invisible dimensions curl and twist in their eternal geometric configurations. All of this happens without your awareness, without your effort. The universe knows how to be itself. It doesn't need your consciousness to guide it. And you can let go, trusting that reality will continue whether you're awake to observe it or not. Let go of the need to understand. Let go of the need to figure everything out. The mysteries will still be there tomorrow. The hidden dimensions will still be hidden. The questions will still be questions. But right now, in this moment, you can simply rest. Simply be. Simply allow yourself to drift into sleep, cradled by 3-dimensional space, surrounded by however many extra dimensions might exist, held by the universe in all its mysterious complexity. Your breathing is slow and steady now. Your body is heavy and relaxed. Your mind is quiet, thoughts drifting by like clouds, observed but not grasped, present but not important. And somewhere in that quiet and that stillness, you begin to let go of waking consciousness. You begin the gentle transition into sleep, into dreams, into a different mode of being, where the usual rules don't apply and anything is possible. Maybe in your dreams you'll experience what it's like to move through extra dimensions. Maybe you'll see geometric spaces that can't exist in 3 dimensions. Maybe you'll understand in some wordless, non-rational way what it means for dimensions to be curled up at microscopic scales. Or maybe you'll dream of something else entirely. of flying or falling or walking through familiar places that are somehow transformed. Dreams have their own logic, their own geometry, their own dimensions that don't follow the rules of waking physics. And that's appropriate. Because if our physical space can have hidden dimensions, why not the space of consciousness, of dreams, of imagination? Why not accept that reality in all its forms is richer and stranger than our everyday experience suggests? So go ahead and dream. Dream of extra dimensions if they come to you. Dream of strings and brains and Calabi-Yau manifolds. Or dream of something completely different. It doesn't matter. The important thing is that you're resting, that you're allowing your mind and body to recover from the day, that you're trusting the natural process of sleep to restore and refresh you. The hidden dimensions will still be there when you wake, still hidden, still mysterious, still waiting to be understood or to remain forever beyond our grasp. The universe will still be vast and strange and wonderful, and you'll be part of it, as you've always been, part of this magnificent, incomprehensible reality, moving through visible dimensions and invisible ones, made of particles that are perhaps really strings, living in a space that might have far more to it than meets the eye. Rest now. Rest deeply. Let the wonder of it all surround you like a blanket, warm and comforting. You're safe here in this three-dimensional space, cradled by whatever extra dimensions might exist, held by the universe that brought you into being and sustains you in every moment. Sleep well, dream deeply, and know that morning will come, bringing with it new questions, new discoveries, new mysteries to ponder. But for now, there's only this: breath, body, rest, and the infinite mystery of existence in all its dimensions, seen and unseen. Good night.